I know some of you asked to see the solutions to the wheel, or the car wheel task, and so here they are. First thing is just really understanding the dimensions of the wheel and then how it's turning when the car starts going. The distance from the center to the point P, which is at the starting point on the ground here, is 1.2 feet. And so that means that this distance is 1.2 feet, this distance is also 1.2 feet, and so the total distance from the top to the bottom will be 2.4 feet. So those are a couple things to note, and that will be pretty important as we move onward. 1.2, and then the total distance is 2.4. And then we're told that 0.4 seconds later, after the car starts driving at a constant speed, and this is important because we know it will always be turning the same number of times around every second, since that's what constant speed means. After 0.4 seconds, you record that the point P has now returned to the ground. So in other words, 0.4 seconds go by, and after 0.4 seconds, your wheel is in the same position again, where point P is now again at the bottom. In other words, it's touching the ground. Alright, so that's the information we start with, and now let's get into the questions. So the first thing that we want to do, and you'll probably be able to guess what we want to do here, is we want to model the height of this point P above the ground over time. So just to get an idea of what this is saying, time 0, your point P is on the ground. And as the car wheel starts rolling, and you can imagine it rolling this direction, the point P will eventually start getting higher and higher off the ground until at some point it's going to be at its maximum height above the ground. Maybe that occurs halfway in between here, 0.2 seconds. And then after 0.4 seconds, it's rolled all the way back to the point where it's at the bottom of the ground. So its height is going to increase and decrease between 0 and 2.4, and it's going to repeat this pattern, and the pattern is going to look the same because we're traveling at a constant speed. And so we can identify this as a periodic model, and we can use a sinusoidal function. So you all know the basic form of a sinusoidal function, and we can just call this function, we'll call it h of t, the height in terms of the time. And so now we need to decide what the parameters should be to accurately model this situation. So we'll have some amplitude. We'll choose either a sine or a cosine function, depending on which is easiest. We will need to pick a parameter value for b. That will, of course, be determined by the period. Our input variable, of course, our independent variable is t here, and we may or may not have a phase shift. Of course, we'd like to avoid having a phase shift by picking a sine or cosine function, depending on where the initial value is. And then, of course, we will have the midline. Okay. And so, pretty easy for us to kind of pick these apart, and of course start with the midline and work our way towards the amplitude and so on and so forth. So the height above the ground will go between a value of 0 and a value of 2.4, meaning that the midline will be a value of 1.2. So our k value here is going to be 1.2. And the amplitude is, of course, the amount that you can go above the midline or below. And so the amount you could possibly go above will be 1.2, or you could go 1.2 below. And so my amplitude is going to be 1.2. Now thinking about the period, and this might be one of the trickier pieces if you don't draw out this picture, is to understand that it will make one full rotation every 0.4 seconds. Meaning that the value of point P, its distance above the ground, will go through all of the possible distances above the ground in 0.4 seconds and return back to the ground. So the period is 0.4, and we know that the period is equal to 2 pi over the value of b. And so we can solve for b. b is simply 2 pi over 0.4. Now, if you left it like that, that's perfectly fine. Or if you type this in your calculator, you would find that this is 5 pi. You could leave it like that. or you could simplify even further to the point where you get 15.7 as the approximate value for the period. I'm just going to go ahead and use 5 pi since we like to keep everything in terms of pi to make it most precise. So my b value is going to be 5 pi. The next piece is to decide whether we want to use a sine or cosine function and if we need to implement any phase shift to do so. So remember, we look at the characteristics of a sine and cosine function with no phase shift. We know that a cosine function with no phase shift has a y-intercept at its maximum value and then will decrease, meaning that a cosine function with no phase shift would have an initial value where p is 2.4 feet off the ground and then would decrease. Okay? And unfortunately that doesn't quite work. We have the exact opposite situation where we have an initial value where p is at a minimum and then it starts to increase in value. And so what we can do is, instead of using a cosine function, we can use a cosine function and multiply by a negative, because multiplying by a negative will reflect. And so what I will do is, now instead of 1.2 I have negative 1.2 cosine. My b value is 5 pi times t plus 1.2. And that is going to be my function h of t. And I can kind of go through and explain why this function is accurately going to model my situation, right? To start off with, we know that the initial value when t is 0 is going to be exactly what we want. We can go through that. So plug in 0, we'll have cosine of 0, which is 1. Negative 1.2 times 1 is negative 1.2, plus 1.2 will be 0, and that's of course where the point P starts. And you could go ahead and show that 0.4 seconds later, if you plugged in 0.4, you get 5 pi times 0.4, and you'd find out that that's 2 pi. Cosine of 2 pi is 1. 1 times negative 1.2 is negative 1.2, plus 1.2 is again 0. So that should suffice for your explanation. And now we need to sketch a graph of the function, and honestly, this is probably the easiest part because you don't even need to have the perfectly correct function written out to graph it correctly, because you have a description that will allow you to do so. The key here is to make sure that we label all of the values appropriately. So my y-axis, which is going to represent the height, I would probably put 1.2 in the middle here, and then 2.4 up here, and then make sure that I label this as time. And then I can just go ahead and sketch this out. I know that the point P is 0 feet off the ground when time is 0, and then 0.4 seconds later it's going to be in the ground again, and so it will, so on and so forth. And so there you have it. Pardon my minor issues with actually drawing a smooth curve, but that is approximately how it should look. Now we want to calculate the car's speed in feet per second. And here is where we need to call upon a rational expression or rational equation, which tells us, and we should remember this, that speed is the relationship between the distance you've traveled and the time it's taken you to travel that distance. And so we want to think about, okay, how do we know how far the car's traveled just by knowing how the wheel turns? And to illustrate this, and this should have been sort of intuitive, but if you drew it out, it would have really helped, and I saw some people draw some great diagrams. Roberto Miranda comes to mind, of looking at how, as your wheel turns, how much of the wheel has touched the ground. So at the beginning, our point P is right here. And let's just imagine that the wheel has turned, and now point P is at this place, right? How much of the wheel has touched the ground? Well, if you think about point P starting here, and as the wheel rotates in this way, all of this part of the tire must have hit the ground. Okay? And so that means the car has traveled that distance. Well, when the point P has returned to its original position, that means that all of the tire has touched the ground, meaning that the car has traveled this distance, because each piece of it touches the ground and that moves the car forward. So the distance the car travels can be thought of as the circumference of the tire. And so since we know that the car tire turns all the way around in 0.4 seconds, we can find that the circumference of the tire is the distance that you travel in 0.4 seconds. So the speed is going to be the distance, and circumference is 2 times the radius, which is 1.2, times pi, all divided by the time, which is 0.4. So I can plug this into my calculator and find that the approximate speed in feet per second is 18.85 feet per second. Feet per second. Again, the big piece of this is understanding that I measure the distance by how much of the wheel touches the ground. So if I know that the entire wheel has touched the ground after 0.4 seconds, that means that I've traveled one full circumference in distance. And one way of visualizing this is to imagine that you cut the wheel here. So if I were to make a cut in the wheel, and I unrolled the rubber of the wheel, and that distance that you have is the circumference of the circle. And that's the amount of tire that touched the ground and propelled you forward. So that's the distance that you traveled, a full circumference, in 0.4 seconds. Now we need to convert this to miles per hour. So let's first convert seconds to hours. So if you know that you've traveled 18.85 feet per second, how many feet are you traveling every hour? And so the way to make this conversion is to take our 18.85 and we need to convert feet per second into feet per minute. So if this is the number of feet you travel in a second, well, how much of those do you travel in a minute? There are 60 seconds in a minute, so we'll multiply by 60. So now at this point, and we'll just keep track, we now have feet per minute. Okay? And now we want to know in terms of hours. Well, there are 60 minutes in an hour. So however many feet we travel in a minute, we'll travel 60 times that in an hour. So multiply by 60 again, and that will give us feet per hour. Okay? Now, if you have a number of feet per hour, how do you figure out how many miles that is? Well, 1 mile will be 5,280 feet. So if you have a certain number of feet, see how many 5,280 chunks there are, or in other words, divide by 5,280, and you will get the number of miles you've traveled. So I will multiply by 1 over 5,280, the same as dividing by 5,280, and this will now convert me into miles per hour. And when I do that, I will get approximately 12.85 mph, or miles per hour. All right. That was, I think, maybe not, but I think that was one of the trickier questions. All right, so now after the first minute, the car starts to accelerate, right? Means it's turning faster and faster. So the car tire is turning faster and faster. And in fact, the car doubles its speed every 25 seconds over the next minute. Find the speed of the car at the end of the minute of accelerating. So think of it this way. You have some initial speed that the car starts at. And every 25 seconds, you're going to double it. Okay? So we have these initial speeds here, right? This is the speed that it was traveling at. And after 25 seconds, you're going to double it, meaning you're going to multiply by 2. And then after another 25 seconds, you're going to multiply by 2 again. So you're going to have 18.85 times 2 times 2, or 2 squared. And this doubling is an exponential process. So we can use an exponential model to represent this situation. So the speed of the car at any given time t is going to be exponential. So what you're going to do is you're going to take the initial speed, let's call it I, the initial speed, and you're going to multiply it by 2. And you're going to dictate how many times you multiply by 2, and you're going to do that every 25 seconds. So t over 25 as my exponent. And this should make sense because now you know when t is 25, you'll double your speed. When t is 50, you'll have doubled it twice. So just using 18.85, we can round this up to 20. After 25 seconds, you'll be at 40. After 50 seconds, you'll be at about 80 feet per second. Same thing with miles per hour, just a little lower of a number. And so now you can use this to compute the speed. So we'll just plug in the initial speed of 18.85 and a time of 60 seconds, and we'll get that our speed after 60 seconds is going to be 18.85 times 2 to the 60 over 25. Plugging this into our calculator, we get that the speed after 60 seconds is going to be approximately 99.5 feet per second. And if you were to do this in miles per hour, you would get approximately 67.8 miles per hour. So we can see that this doubling process has allowed us to really increase our speed, and it should make sense, right? We just talked about how 18.85 is pretty close to 20. So if we double 20, we get 40. That would be after 25 seconds. After another 25 seconds, we double that to get to 80. And at that point, we've been traveling for 50 seconds. And then we'll travel another 10 seconds to get to 60. And so it won't quite double again. In other words, it won't go up to 160, but it will increase by a decent amount, and it increases to 99.5 feet per second. All right, so now we need to change our function from part A to reflect the new speed that the car is traveling. And so what this means is that now that our car is traveling faster, it's turning around at a faster rate. So it's not going to take 0.4 seconds for P to go all the way around, right? It's going to take much less time. And so what we want to do is we want to understand how we're going to change our period. Now, there are a couple of ways to do this, and I'm going to take you through both of the methods because I think the first one can be a little confusing at first. Okay, so let's just think about the equation that we currently have. Okay, we have that h of t is negative 1.2 cosine. I'm going to leave the inside the argument of cosine blank for a second, plus 1.2. The amplitude isn't going to change. The midline isn't going to change. And look, we could get into it. We could think about where the point P is going to be at this moment after it accelerates for a minute. But you know what? We just want to be able to model the height of the point P above the ground. And so let's just assume, and you could have made this assumption as well, that the point P is again at the ground at the start of this minute, but it's now traveling at this new speed. And so we want to be able to model the height of the point P above the ground now that it's traveling at this new speed. So what we need to do is change the value of our B parameter, right? Because the number of rotations that we make the number of seconds that it takes to make one full rotation have changed, right? We're now going a lot faster. So just think about what this means. If we're going faster, that should mean that our wheel is going to turn around one time in much less than 0.4 seconds, right? Because it's moving faster. And so if we can find this new period, then we'll be able to find the new parameter B. And so let's think about what period means. Period, what we're really saying when we say period, is we're saying the number of seconds per rotation. So we want seconds per rotation. Okay? That's what the period is, the number of seconds per rotation. So how can we figure out the number of seconds that it takes to make one full rotation? Well, let's look at what we already know. We know that one full rotation means that your car has traveled a full circumference. And a full circumference, right, is 2.4 times pi, or 2 times 1.2 times pi. That's the distance of one full rotation. And we know that every second it travels 99.5 feet. So the question is, if this is how many feet you travel in a second, how much time is it going to take to travel 2.4 pi feet? And the way that we can compute this is by dividing. So we can take the number of feet in one rotation, which is the circumference, 2.4 pi, and this is, I'll write this in black, this is the number of feet per one rotation. And we can divide it by the total number of feet per second, or 99.5 feet per second. Okay? And when we when we divide by something, we're multiplying by the reciprocal. So we'll have 2.4 pi feet per rotation times 1 over 99.5 seconds per foot. Okay. Remember, this is 99.5 feet per second, so when I take the reciprocal, 1 over, what I'm finding now is the number of seconds it takes to travel 1 foot. So when I multiply this out, I have feet over feet, which cancels out, and I'm going to be left with some number which will represent seconds per rotation, which is, of course, the period. Okay, and this is going to be 0.076. And so that is the period. That's the number of seconds it will take to rotate one time. And this should make sense because 0.4 was the previous period, and 0.076 is a lot less time than 0.4, so it's going around once in much, much less time, which is obviously indicative of a faster speed. And so with this being the period, we can compute the b value, similar to how we did in the initial step. And what we will get is that our b value is going to be 2 pi over 0.076, which is approximately 26.32 pi. Okay? So that's going to be our b value. Put that right there, and our independent variable is still time, and that will be our new equation with the updated period. Okay? Alright, now I promised I would take you through one other method, and this method is very similar, but kind of as a couple more steps to it, might be easier to understand. If I am building this new function, I need to find the b value, and so I need to figure out the period. And it still starts by just understanding that the period is the number of seconds for one rotation. And so what I can do first is think about, okay, I know how many feet it's traveling per second, and I know that every time it travels one circumference distance, that is a full rotation. And so a circumference distance, as we already computed, is 2.4 pi feet. And so what I'd like to know is how many of these circumferences does my car wheel travel in 1 second. In other words, divide 99.5 feet up into these chunks of circumferences and see how many full rotations I go through every second. And so that will be 99.5 divided by 2.4 pi. This is going to be the number of rotations per second. And that is going to give me 13.2 about. That's the number of full rotations every second. So now you're thinking, okay, if that's how many full rotations take part in 1 second, I need to divide that 1 second up into 13.2 equal parts. to find the number of seconds it takes to make one rotation. And so to find the number of seconds per rotation, I just do 1 over 13.2, which is 0.076. And this is now the number of seconds it takes to make one full rotation, right? If it travels 13.2 rotations in 1 second, it will take 0.076 seconds to make one full rotation. So that's our period, and we can use that period to find the b value, or the parameter for b. All right, that was a lot. This was a tricky question. Don't beat yourself up if you didn't get all the way through, particularly through parts D and E. But certainly it would be a good one to keep in your toolbox if you ever encounter something similar again.